So let's talk about the different types of solid electrolytes, sort of like a review of what is out there. So first, let's focus on, well, solid electrolytes are primarily used as separators. So the existing separators are not conductive to lithium ions. Solid electrolytes are next generation electrolytes which can make separators because they're solid. These are the properties and a picture of the currently existing separators. They are polyethylene or polypropylene sheets, which are highly porous, about 15% porosity. And in those pores, you include the liquid electrolyte. So basically, the conductivity of the liquid electrolyte in bulk is very high. It's about 10 millisiemens per centimeter. But when you put it inside the separator, it drops from 10 down to something like 0.1 millisiemens per centimeter. So we're talking about a 100x decrease in conductivity because the material from which the separator is made is non-conductive to lithium ions. It's polyethylene, polypropylene, has no conductivity whatsoever. The only conductivity through the pores of the liquid electrolyte, the pores of the separator, is given by the liquid electrolyte. Okay, so the next generation to this are solid electrolytes. Solid electrolytes offer this sort of geometric separation of the anode and cathode. You never want the anode and cathode to touch. If they touch, you have an internal short. But instead of the non-conductive polyethylene, polypropylene, you have now conductive species, and they can be polymers. There are three general classes: polymers, glasses, or ceramics. And now you have separation of anode and cathode. You don't need to use liquid electrolyte any longer because these materials conduct lithium ions natively. Okay, so the oldest or first sort of with the richest history are polymers, but these are conductive polymers. They are not polyethylene or polypropylene as used in the legacy system. This is a type of material, a type of polymer called PEO, polyethylene oxide. It was first shown to conduct lithium ions. So if you mix PEO with lithium salts and you dry off the solvents, you're left with a solid solution of lithium salts and the polymers. So that's been shown since 1973. So now you can have a solid separator, which is polymer-based, and conducts lithium ions without the need for any sort of solvents, without the need for liquid electrolytes. The problem is that the conductivity of this type, is about 100x smaller than what you get from the legacy option. So you have to heat up the battery in order to make it work. But it's the only option out of the three here, the only type of material that has been commercialized. It's been commercialized since 2010 by Blue Solutions, and they make large pouch cells for EV with this type of chemistry. Okay, this material is inert. Polyethylene oxide does not react with oxygen or water. You can handle it in open atmosphere, easy to scale. It's nice, and it's a polymer, so it's the mechanical properties are very good. It doesn't break. It's soft. You can bend it. The problem is, of course, it needs a hot battery to operate. You need to heat it up. It has another problem. It's not stable high voltage cathodes. You can only use low voltage LFP type of cathode. You cannot use NCN, NCM. Big advantage is not reactive, as I discussed. It's easy to scale. The only one that's been demonstrated commercially, and it's highly flexible. So you can make all sorts of cell formats with it. Okay, and I put here the cell formats. Any cell format is attainable if you use this type of separator, just like it is if you use the commercial system. They're both polymers. All right, let's talk about the next class, glasses. Glasses are more new. They really took off after about the year 2000, but they've been shown ever since the 80s, especially sulfide glasses, so glasses based on sulfur. Very high conductivities. So in the bulk, recently, in the past 5 years or so, they have higher conductivity than the legacy. But the problem is there's several issues with it. First of all, it's based on sulfur. So what happens? Sulfur-based materials, they easily react with moisture, and you make all sorts of very dangerous gases when you react with moisture. You can make acids. You can make like sulfuric acid. You can make H2S gas. Both of these are very nasty to work with. So it's very difficult to scale. Also very difficult to contain if you have sort of a cut or like a crash of any sort and the battery is exposed to moist air. That's a problem. It's not safe. The reactivity of this material inside the battery is very high. So it's not stable electrochemically inside the battery. So people have gotten it to work with 3 volts and 4 volts cathode, but not natively. There are coatings, protective coatings applied to the cathode to make it work. That's how they got around that. It reacts with ambient atmosphere. Actually, these glasses contain phosphorus in addition to sulfur. LPS stands for lithium, phosphorus, sulfur. So sulfur reacts with moisture, phosphorus reacts with oxygen. So you cannot operate this material even in dry air. Very difficult. So people do operate in dry air, but you have a huge drop in conductivity. So if you work with it in a glove box under argon atmosphere, everything is nice and high conductivity. If you operate in the dry room where you got no moisture, it's safe, but conductivity drops significantly below the conductivity of the commercial systems. And it's very difficult to scale because when you scale, you cannot operate in specialized gas atmosphere. You have to operate in open air, sometimes moist, wet air, and you can't do. It is ductile, which means that it can be pressed and forms very good interfaces. So this is the issue with this material. And companies like Toyota, companies like Solid Power have focused on this material. But these are the issues with this material. The most modern are the modern ceramics, specifically LZO. This was demonstrated since the 2007, 2008, I have seen, Max Planck Institute. This is a ceramic. It is very inert, which is good. That doesn't react with anything. It has been shown, however, that exposure to water creates some passivating layers, which reduces conductivity. So even though initially it was thought it's inert, actually in practice, when it is prepared and manufactured, you got to keep it very dry. So that's an issue. Conductivity is on par, if not a little bit higher than the legacy, but conductivity is lower than the glasses. Uh, it has very high electrochemical stability inside the cell, so you can work it with 3 volts, 4 volts, 5 volts, perhaps up to 10 volts if you have such cathodes in the future. But unlike the sulfides, which are soft and ductile, these are hard and brittle. So it's very challenging to obtain separators from this material which are thin and which they do not break. So that's a problem. Because they're so brittle and ductile, you can only make pouch cells. You cannot get wind formats because you cannot bend this material too much. You can bend it to some angle, sort of like the flexibility of a credit card, but not more than that. Two major issues with these two classes is that they're heavy. So it's very difficult to get high energy density out of them. So they're between 3 and 5 times heavier than the legacy system. And you got to keep in mind about 30% of the volume of a cell, of a lithium-ion cell, consists of electrolyte. So if you make this type of conversion from legacy to these type of materials, and all of a sudden 30% of your cell is 3 to 5 times heavier than before, it's very challenging to obtain high energy density in these batteries. This is something that is not talked about so much, but it's a huge impediment to obtain high energy density. And of course, we have our material. The thesis of our company is ultra high energy density, above 600 watt-hour per kilogram. So we cannot play around with glasses and ceramics. No, sir. You can only do liquids, or we can do polymers. The polymers and the liquids have very similar type of density, so you can use either one. Given that you solve the issues that exist with the existing conductive polymer, which is PEO, and we have solved such issues. So our proprietary polymer, it is much more conductive. It is not based on the same chemistry as PEO. PEO is basically a polymerized ether. We polymerize carbonates, so we have much higher conductivity, and we also have high inertness. Our materials are inert in the sense they do not react with water, they do not react with air. It's a polymer, same properties as the PEO, as the polymer that we discussed previously. Because it's a carbonate and not an ether, it's natively stable with high voltage cathodes. 3, 4, 5 volt cathodes work with this type of polymer because it's a polymerized carbonate. This is new, okay? And it has very high native stability. So the two major issues that PEO had, low conductivity and instability with high voltage cathodes, we have solved. So it's easy to scale because it's not reactive. It's highly flexible, as we have discussed. You can wind it or wound it, and you can make jelly rolls with it, things that you cannot make with ceramics. So any cell format is within reach. So this was the overview.